Hopefully everybody's ready for the enormous GIL talk here. So I'm Dave. What we're going to do in this talk, I'm assuming that a few of you know that Python has this global interpreter lock. A couple of people have heard of that. I think there should be like a module corresponding to the import this. This is the import that, the things that you're not supposed to talk about, and the GIL could be on that list. So, big thing with the GIL, people know that it limits thread performance, and because of that, it's this source of you occasionally see contention on like news groups and blogs and things about it. And so in this talk, we're gonna talk about it. To introduce the talk, I wanted to show a demo first, just to set up why I'm interested in it. What I'm going to start with is this is just a dumb program that just spins for a bunch of calculations in a single thread, basically. So this is a little countdown program that does 50 million iterations of some task sequentially, and I just time it and see what happens. If you run that, took about 5 seconds when I tested this out this morning. Okay, so 5.4 seconds. And what somebody might be inclined to do is spread work across threads. I mean, this is a common parallel programming idea where you take a bunch of work, you just subdivide it across 2 different threads, and then you hope that it runs twice as fast. Now, because of the global interpreter lock, I mean, people here probably know that, well, it's not going to run twice as fast. It'd probably run maybe at the same speed. And it turns out that the result of doing that is actually kind of surprising. So if you run this parallel version of code, it takes a little bit of time here. It takes about 10 seconds. And if you know a little bit about threads, that's not the kind of result that you want to see. I mean, okay, 2 threads, twice as slow. And then things get really bizarre. So I don't know whether the Mac users know this, but there's a preference thing that you can install to disable one of your processors. It actually comes with Xcode, so it's not it's not normally installed, but there's this tool where you can go on there and say, well, okay, disable one of the cores on my laptop here. And if you do that and run the same thread test, you get this really sort of remarkable outcome. So we'll see what happens here. Okay, so it runs a little bit faster, having one of the cores disabled. And then I have this is my special Python version of this. I tested out. If you write a Python program, this is spin.py, and all it does is just loop in a while loop. If you write a version of the threaded code, so this is a new version where the first thing I do is I launch spin as a sub-process, and then I launch 2 threads and do the same thing before. So if I run that one, so keep in mind, this is like 2 threads and a useless sub-process hammering one of the other cores. Let's see what happens here. It runs even better, okay? So, bring that up at your next code review. It's like, I have this idea for a performance optimization. So what this talk is about is what in the hell is going on with that. So we're going to look at the global interpreter lock. We'll see some cool pictures. We're going to look at the new global interpreter lock in Python 3.2 that Antoine has implemented. And just as a disclaimer, there is an earlier version of this talk that you may have seen on the web. This talk that I'm doing here is different. And I also have to make the disclaimer that I'm going to go really fast through some of this material. So I want to look at some demonstration stuff later. So I have to cover a little bit of essential background first, and then we'll get into it. So the first thing I want to do is just cover a little bit of background about how Python actually works, and then we'll get into explaining why it does that thing that was in the demo there. So the first thing that you need to know, Python uses real threads. A lot of people are kind of misinformed about this, but Python interpreter uses POSIX threads, Windows threads. The interpreter is fully threaded using pthreads. But as we know, there's this interpreter lock in the implementation that basically prevents parallel execution. So the reason that is there is to simplify the implementation of the interpreter. I mean, there's lots of things that simplifies, like memory management, C extensions, various other details of the interpreter. And the primary outcome of the GIL is that instead of parallel computing, you get cooperative multitasking. I mean, that's essentially what the GIL does to your program, is that when threads are running, they'll run until maybe you do like a read or a write or a send or a receive or something like that. And when you do I/O, a thread will give up the GIL, and then some other thread can then do something for a while. So the whole idea with the GIL is that you're going to get threads that just kind of alternate between each other, and if they do I/O, then they sort of stop for a moment. Now, the tricky bit is that sometimes you have threads that just don't give up the CPU. I mean, this is the classic, CPU-bound thread processing that will just sit there and hammer and hammer and hammer on the processor. And the interpreter actually has a check to deal with that. There's this so-called check that takes place every 100 ticks. We'll say what those are in a second. So if you have a thread that's just hammering on the processor, it's running along, and then every 100 ticks it does this mysterious check. What is going on there is that a tick in the Python interpreter is loosely one machine instruction. So if you look at the low-level sort of bytecodes that the interpreter is running, those are sort of what ticks are. One thing I'll mention, they're not based on time. So some of these ticks actually take longer than others. Like if you call into like a big operation in C, a tick might take half a second or something to run. So the timing is highly variable there. And then as far as what that check is, it's really, really simple. All this check does is it just resets the counter back up to 100. So keep in mind this little check takes place every 100 ticks. There's a little bit of signal handling if you're the main thread. And then a thread will just give up the GIL and then try to get it back. And that's actually all that happens. This is actually what the C code for thread switching looks like in Python. I've kind of cut out a few of sort of essential bits, but essentially every thread that you create in Python is running some kind of loop in C that looks exactly like this. It's like decrement the ticker. If it's less than 0, reset it, and then you have this little bit at the bottom that just give up the lock, get the lock back. There's nothing else to thread scheduling in Python. There's no scheduler, there's no magic algorithm, there's no secret module off in some directory somewhere. So that is basically, that's essentially the extent of thread switching in Python. And the question is how is that responsible for making a program run twice as slow? I mean, I'm just not seeing a whole lot there. I mean, it's like, what in the world is actually running there to hammer your performance like that? And so to find out, there's sort of two things that we have to do. What I'm going to do in this next section is just briefly talk about how thread switching actually works in Python. And then we're going to do a little sort of analysis of it so you can see it in action. So the way that things are put together, Python, the C interpreter, actually only implements one type of lock. And that lock is actually used for everything. Like all those objects in the threading library, like rlock, event, condition, semaphore, lock, all that stuff is actually based on this one lock. And it's not actually what most programmers would think of as a lock. I mean, I think a lot of people, when they think of a lock, they think, like mutex lock. That's sort of the most familiar kind. And the GIL, or the lock in Python, is not a mutex lock. It's actually something known as a binary semaphore. And this is sort of what the implementation looks like. It actually has it sort of has three parts to it. There's sort of there's an integer sort of status that just indicates what is the state of the lock. 0, it's available. 1, it's locked. There's a pthreads mutex that just protects changes to that. And then there's a condition variable that does some signaling. So going through all of this, I mean, I apologize if it's bringing back like a bad memory of an operating system class, but this is, this is the kind of thing like a professor would spend like 2 weeks or 3 weeks talking about with like thread scheduling. But this is essentially what locks are sort of doing in Python, is kind of messing around with this mutex and this condition variable. And probably the most critical part of it is the way that a release hands off the GIL to another thread. Essentially, it's based on this signaling mechanism here. It's a little bit subtle, but if you release a lock, a thread will actually send a signal to some other thread saying, hey, I gave up the lock. You're free to run now if you want to. So that's kind of the critical piece there. And the way that this manifests itself, so this is how thread scheduling kind of works in Python. If you run 2 threads, so let's say you have some thread that's just sitting there hammering on the processor, and then you have some other thread that wants to run, but it can't because it needs the GIL. There's sort of 2 different cases that come up. The easy case is that the thread 1 just goes away. So like if thread 1 is running and then it has to read off a socket or something, it will essentially just release the GIL and then go to sleep while it waits for data to come in. So what happens there is this thread will send a signal into the pthreads library, and through some complicated mechanism that we don't really have to worry about, that gets the operating system to switch to the other thread. Okay, so that's kind of the easy case, is that if you do I/O, the system signals the other thread and says, okay, go ahead and run. The tricky case is actually the one where the original thread runs until that check. So let's say you're running, and you're running and running and running and running, and then you hit that check interval. What happens here is that the interpreter forces the thread to give up the global interpreter lock, and you get this situation of what happens afterwards, because technically at this point, either one of those threads could continue running if it wanted to. And so what actually happens here is you have to know a little bit about how condition variables work in the operating system. It turns out that condition variable that the GIL uses is built largely around a queue of waiting threads. So if you wait, like let's say a thread comes in and says, I want the GIL, it actually gets sort of deposited on some queue somewhere in the pthreads library. And then it will sort of wait there until it gets popped off by a signaling operation. So in many cases, this is just kind of like a FIFO queue that gets built up in pthreads. And if you go on there, it will take a certain number of signaling operations to come off. And what happens when you get popped off, so let's say you get signal, you essentially enter the operating system run queue or the ready queue, and then you fight with all of the other processes and threads that are running. So if you signal a thread, it will sort of go compete with everything that's going on in the operating system, and then the operating system will just run whatever it thinks it should be running at that time. So what may happen is this thread 1 might release the GIL, but then the operating system just gives it right back again, because it essentially says, well, thread 1 has the highest priority, so I'm going to keep going. So that's one case that might happen. The other case that might happen is the operating system might say, well, this new thread actually has higher priority, so I'm just going to run it instead. So the key thing is that whatever has the highest priority is actually going to win this battle over who runs next. And that's actually not anything that you have control over as a Python user. I mean, essentially, the operating system is monitoring threads as they execute. It's setting priorities. I mean, there may be some kind of magic system call that you could use to like mess around with that. But generally, as a Python user, this is outside of your control. So this is all going on in the operating system. So again, I apologize if that was like the world's fastest coverage of operating system scheduling and condition variables there. Now, what I want to talk about, now this is where it starts to get interesting, is this business of what can go wrong with that. Because we definitely saw this crazy behavior when we started off the talk. And to get a handle on this, I took a version of Python 2.6 and instrumented it with some logging. And what the logging was meant to do is record a huge trace of like when threads got scheduled, like when did they get the GIL, when did they give up the GIL, when did they try to get the GIL but couldn't, and so forth. And really the goal was to get kind of an idea of how, what is going on with threads in the interpreter. This is sort of a general idea of the logging. I had to introduce an extra counter to keep a little bit of a history of the log. And then what happened is in the locking, I added some operations to basically log events. This is just some pseudocode. I mean, this is actually all implemented in C. And you can, actually, I describe it on a blog post. So if you want to ask me about it or look for it, you can find that. And then what the outcome of this is I got these huge traces basically saying, well, here's a whole bunch of events with like different threads, timings, like is it acquiring, is it releasing, is it busy, and so forth. So what I want to do is actually show you some of this stuff because it's pretty interesting what goes on. So what I found in the logs is that there's sort of interesting behavior on one processor, but it gets insanely diabolical on two. So I have this visualization that we're going to look at. It's actually on the web, so it's set up that everybody here can go there and actually interactively kind of explore. This is something that I generated with about 2 gigabytes of log data, and there's about 2 million PNG image files sitting behind this visualization. If you want to know how I created that, I wrote some custom Python tools and used the multiprocessing module to render it. So that's my big plug for multiprocessing there. So let's go take I'll take a little tour of that. And I'm gonna kind of maybe point out some highlights. Oh, I'm not even on the internet. Okay. I do plan for such. Let's just turn it off here. Oh no! Oh no! Okay. Okay, hold on just a second here. The best laid plans go bust here. Okay. Okay, that actually was set up. Okay, so hopefully people can get to that, and I have it running in the wrong directory. This is what I love about live demos. It's always a bad idea. Always a bad idea. Okay, so hopefully the website, is the website working for people out there? Okay, so what I'm going to show in this demo, I have these sort of visualizations that actually show different thread scheduling. I'm going to just briefly talk about the legend first. What is showing is black basically means that nothing is running. A green bar means that a thread just acquired the GIL and is running. Yellow actually means that a thread woke up and tried to run, but couldn't because the other thread was holding the GIL. It's like a false alarm, kind of, where it's like, oh, I want the GIL, but no, it's not available. And then red is sort of a repeat of a wake up. It's like, oh, I woke up again, but the GIL is just not there. So it's like back to sleep. It's like, it's not there, I got to go back to sleep. Across the top of this are interpreter ticks, so that's kind of like a sense of time. And the number at the bottom is a badness measure. Maybe I won't say anything about that right now. But what I want to do is actually just sort of show you what the behavior of threads are in Python, because it's actually kind of interesting to sort of see what happens. So this is actually what you see for running on one processor. For one CPU, threads actually get a pretty long execution interval when they run. So this is what happens sort of alternating between two CPU-bound threads. They actually run for long intervals of time. If you zoom in on it, you can actually get a sense for like how long these time intervals are. Like that's an interval there that is, well, let's see, we're about 1 million, something like that. I mean, we're on the order of like hundreds of thousands of interpreter ticks that are going by when this thing is scheduling. So what you find on one CPU is that threads sort of alternate over long time periods and just sort of alternate between themselves. That's actually what you want on one CPU. I mean, that's the behavior you want, because if threads were like thrashing, you would end up with all sorts of context switching. So you don't want to do that. So that's what you see on one processor. And where it gets sort of wild is when you start going to maybe two CPUs. What you'll find on two CPUs is that the amount of like switching between threads actually goes up substantially. That's what you see in this this bottom graph here. You're sort of seeing much more rapid switching. And if you zoom in on that, it actually starts turning into a sea of red, which is bad. And if you keep zooming in on it, so this is the kind of the cool part. What's happening here is every single time a GIL or a thread releases the GIL, it signals the other thread that wakes up some short period later, and then it can't get the global interpreter log. What you're actually seeing here are the two CPU cores are like fighting with each other, because if you're on two CPUs, the operating system is basically saying, oh, I can run two things at once. So what it does is it actually keeps the original thread alive, wakes up the other one, and then it falsely can't run. I mean, it can't run because the GIL's not there. So if you kind of look through that data, you see this like wild like thrashing. While one thread is running, the other one is sitting there like thrashing on the other core, burning up like millions of system calls. So that's actually a big reason why you're getting that worse performance. It actually gets even more insane if you go to things like 4 CPUs and 4 threads. This is kind of an interesting one down here. So this is 4 threads competing on like a quad-core desktop. And if you zoom in on that, it's just radical thrashing. I mean, it's like all green, all red, and I mean, what's happening here is it's just like crazy. It's like not only are you getting like insane context switching, but you're getting all sorts of like false wake-ups on the different threads and so forth. So the thing is just like churning on the system with like all these system calls, all this context switching, and so forth. So that's kind of neat. I mean, I had no idea that well, maybe neat isn't the right word, but I had no idea that that was happening. Now, another test that I did about a week ago, I put up a web server, a Python. Before I talk about that, I want to talk about one other thing. Another thing that's actually kind of cool is the handling of events. Like sometimes you'll have one thread that's like running, just hammering the CPU, and then you'll have another thread that just wants to wake up and handle like an I/O event. And if you're on one processor, that's actually what this top plot is showing. Is like a thread that what I've got here is I have like some thread that's just pounding the CPU, pounding, and then like a network packet comes in. And what you see is really behavior like this. If you look at that, there's like a really brief wake up. A thread will just run for almost like nothing, like maybe like 2 ticks, 3 ticks or something like that, and then go to sleep. If you try that same thing on 2 cores, you actually get another interesting behavior. What you'll find is that like when a network packet shows up, the I/O thread will try to run on the GIL, and then it just sits there and thrashes for like maybe thousands of intervals. So what you're seeing down at the bottom here is a thread that wants the GIL, thrashes, and then it gets it for maybe like 2 interpreter ticks at the end. So this is the kind of thing that would like kill like response time. Like if you were running like threads and you wanted to have like a really quick response on 2 cores, you're not going to get it here because that the thread that just got this event is just hammering, sitting there on churning essentially. And then kind of a final thing, this is something to look at. About a week ago, I put up a Python web server on an EC2 node, and then I put out a tweet asking everybody to hammer the hell out of it. The reason I did that is that conventional wisdom with the GIL is that it really only applies for like this CPU-bound stuff. It's like I/O-bound threads. I/O-bound threads work great. And I was actually kind of curious to know whether I/O-bound threads would actually thrash like that. And the short answer is that they do. So this is a plot of about 1.6 billion interpreter ticks showing a 512-threaded web server. And if you zoom in on it quite a bit, I mean, you actually see like tons and tons of things happening. But if you go into like close enough resolution, you actually do start seeing like waves of like red and yellow, which are indicating like essentially the cores fighting with each other as like the load gets high. So on these I/O-bound systems, you'll actually see this sort of thrashing going on, although it's a little bit more difficult to kind of get that to happen. So I would say, kind of look at you can kind of play around with those plots, but it's sort of interesting, that on multiple cores, you just get like this battle going on. There's like all these like false wake-ups and context switches and so forth. Now, what I want to do in the last little part here, I want to talk about the new GIL that has been implemented by Antoine. So this is something that's only available in Python 3.2. And it's something that aims to solve that GIL thrashing. And as far as I know, it's the only major change to the GIL since like 1992. So, I mean, I think that deserves like some applause to even like, to sort of tackle that. I mean, I actually downloaded like Python. I don't know what the oldest version available on python.org is, but the code in that version is the same as in Python 3.1, basically. So there has not been a lot of change in this. And so the way that this new GIL works, it's a totally different concept. Essentially, all that tick interval stuff is gone. So you just forget about that. Essentially, there's just a global variable in the interpreter that just says, drop the GIL. And kind of the idea on this is that a thread will run until that gets set to 1, and then it just drops the GIL. Now, the way that this actually happens is that a thread will run. So you launch a thread, and it'll just run and run and run and run and run, never doing anything. And so that's fine. But what happens is if a second thread shows up and wants to run, you kind of get a situation like this. So one thread is running, another thread is suspended because it doesn't have the GIL. And the way that it gets it is it essentially does a timed wait. So this is a totally different approach to the problem. Essentially, thread 2 will wait for a certain timeout, saying, well, I want the GIL within 5 milliseconds. And the idea here is that this thread 2 is either going to wait for thread 1 to do I/O. So this is the good case. It's like, well, maybe thread 1 is going to do a socket read or something pretty soon, in which case I'll just get the GIL some point, soon. If that doesn't happen, what essentially happens is thread 2 will set this drop request, forcing thread 1 to stop. So what happens here is if this request gets set, the running thread just immediately stops after it's finished whatever instruction it's doing, and then it signals thread 2 saying you can go run at this point. So. And then the last little bit is that when this thread starts running, there's a little bit of a signaling mechanism built into it to avoid this like GIL warfare thing that's going on the cores. So that's kind of what the new GIL is doing, and it actually works. I mean, it's pretty cool. You can try it out. So I did this on a quad-core Mac Pro, just trying different threads. And the performance goes up a little bit over sequential, but it's actually a lot better than what you saw before. I did some tests even as high as like 100 threads, and it was very, very like stable doing that. So this is this is really great. I mean, this is like to see that. The only problem is it doesn't quite work. So this is this is the GIL part of the talk here. It turns out that there is a diabolical impact on I/O performance in certain cases. Let me just kind of describe the setup. Let's say you had a thread that's doing some kind of work. We don't know what it is, but it's kind of churning on the CPU. And let's say you have another thread that's doing networking. So in this case, it's like an echo server that's doing something. Maybe a scenario to think of here is maybe you're trying to overlap CPU processing and I/O in some way. I mean, this is a very common parallel computing thing where you're going to be churning on some kind of problem, but then receiving I/O messages in the background. And it turns out that there's some subtle bad behavior of that with this new GIL. One of the problems is that if this thread 2 is supposed to handle like an event, like let's say it's like a really short event or a data message coming in, it doesn't actually. When that arrives, it essentially starts the timeout process from the beginning at that point, and then it gets the GIL afterwards. So one of the things that will happen is there's this huge timeout period of 5 milliseconds by default that it won't be able to run. So how this would manifest itself is like a poor response time for that I/O processing. I mean, essentially you're stalled out waiting for the thread 1 to timeout. The other thing that's a little bit more maybe subtle is it turns out that the way that this is implemented, a thread that does the timeout is not often the one that gets the GIL. And this actually has to do with the way that queuing works in the OS. But you may actually get a situation where this thread 2, it's the one that wants to handle the event. It does the timeout, and then some other thread ends up getting the signal saying that you're going to run. So that's a little bit bad. And then the other thing, and this is something that I guess should have made sense, but it didn't really occur to me at first. Turns out that a lot of the I/O operations that you do in Python don't actually block. This is a fundamental assumption on threads, is that when you do I/O, you give up the GIL because you might block. Turns out that a lot of I/O operations actually do not stop running at all because the data is already buffered in the operating system. Like when you do a write, there's some write buffer that can immediately hold it. Same thing like if you're reading from a file that might be stored in the disk cache already. So there's a lot of I/O operations where what happens is you'll do some I/O, give up the GIL, and then that I/O operation will just run immediately. And then you'll come back and want to run again. The problem is on multiple cores, you end up, this is something known as a Convoy Effect. I mean, essentially what can happen is when you give up the GIL, the CPU-bound thread immediately steals the GIL away because there's another CPU core. And then all of a sudden you have to go back to timeout. So you can end up with this like weird convoying of I/O. And it does actually manifest itself. So I tried a little experiment. Where I had like an echo server competing with some CPU-bound processing where I tried to echo 10 megabytes across like a UDP socket. And what you're seeing is that in Python 2.6, it takes, like half a second. Python 3.2, all of a sudden we're up to like 12.4 seconds. And then we got this like really crazy result. If I added like another like CPU-bound thread into the system, the time shot up to like 46. This is what I don't understand. The Python 2.6 time got better. It was like, that's like probably a whole nother talk as to why that is. And then Python 3.2 shot up to like 47 seconds. And then like the extra icing on the cake is that if I turned off one of the cores, it went down to like 0.14 seconds. So So, okay, so the head is completely exploded as to what's happening there. So I think that the score right now is that. So you might look at that and say, okay, this sucks. I mean, is there any way that this erratic behavior can be fixed? And I think there's a way to do it. I'm going to make this a caution, this is a cautious yes, maybe it might work kind of idea. And it's based on the idea that this timeout idea in the new GIL is great because it actually opens up an opportunity to add a few extra things into the picture. And so one of the things, there's two things that you could add, and I'm going to talk more about this in a second. I think if you could add a priority scheme to separate CPU-bound and I/O threads from each other, you could partially fix the problem because Python would know that some threads are supposed to run immediately and others are going to run for a long time. And then if you have a preemption mechanism where you just allowed high-priority threads to steal the GIL immediately, you could improve that response time. And it turns out that this is actually a solved problem in operating systems because this is what OS kernels do to set thread and process priorities. If you're in an operating system and you say, okay, here's a process that's going to run, the operating system will sit there and monitor that to see whether it exceeds its time allotment. I mean, essentially, an operating system will say, you get 10 milliseconds to run, and I'm going to watch and see what happens. And generally what a system will do is if the time slice gets exceeded, you run for your full 10 milliseconds, and I have to time you out and yank you off the processor, a process will get penalized for doing that. So what happens in a system is the priority will drop if you keep getting timed out. On the other hand, if you give up the CPU voluntarily, maybe doing a system call or blocking or something like that, you actually get a bonus. So you get a bonus in your priority. And so one thing that you might think about doing is, can you apply that to the new GIL? I mean, maybe that's, it's a solved problem in kind of OS. I mean, they already do this. The new GIL is actually based on timeouts. So you actually already have the machinery to know whether a thread times out or not because, we're already looking at that. And if you want to talk about that, come to the open space at 4. I've been kind of messing around with this during the conference and hacked sort of a really hacky prototype of this just to see if it would even work at all. And I'm not sure the code is totally operational on all edge cases, but doing it actually did eliminate that I/O problem. It actually kept the CPU behavior the way it was and fixed the I/O problem. So I think if you're really interested in seeing the code and talking about that, come to the open space. So a few final comments, and then we'll do some questions. One thing I think to keep in mind is that this talk has been around one freaking lock. There are these people, I mean, they say, well, just remove the GIL. It's how hard could it be, just take it out. Hey, did you try that patch, Jesse, of just deleting the code entirely, the lock entirely? Yeah, it takes 5 minutes. Yeah, we're going to remove the GIL in a lightning talk later. So there's these people that say, well, how hard could it be? I think, if you look at this, everything that's going on with this stupid global interpreter lock, as far as multi-core, threads and priorities and thrashing and all that stuff, and then you think about taking the GIL away entirely, where the whole interpreter is going to be exponentially more difficult to write and keep track of. This is not an easy problem. The other thing that I want to end with is I don't think you should use this talk as a justification for not using threads. Threads are actually extremely useful in a lot of concurrency problems, and they're actually pretty good at I/O. In that EC2 test that I did, people were hammering on that server. It did not crash or become totally unresponsive ever. I mean, actually, it crashed once when I ran out of disk space. That was when it crashed. So, I think if you know about threads, they are very useful, but I think it is useful to maybe study some of the edge cases. You want to look at that. And the other thing that I'll end with is I think improving the GIL is something that everyone should care about, actually, because, this multi-core stuff, it's not going away. I mean, if anything, it's going to get worse. And there are a lot of libraries for Python that use threads in the background for various things. I mean, maybe you're not using threads yourself, but maybe you're using some package that's using a thread maybe to, I don't know, maybe it's trying to overlap I/O with computing. Maybe it's trying to do some kind of deferred operation or something. I think having good predictable thread behavior would be a really nice thing to have, even if Python does not eliminate the GIL. So that's basically the end of the talk here. So we have about 5 minutes for. I can't believe that I covered 57 slides in 45 minutes. So we're going to have some questions here.
So, as I understand it, all of your tests were done on the Mac. Have you tried other operating systems with other schedulers? Because, the Linux completely fair scheduler is supposed to be completely fair.
Oh, that's a great question. Actually, the problem actually shows up almost everywhere. I did some concurrency classes in Chicago and had students test this out on Linux machines and Windows. It was horrible on Windows, actually. And then I have done some tests. I went somewhere and we did some tests on 16 core, Linux servers and things. It's the same effect. One thing you do find in Linux is that the impact of this is not quite as bad. And I think that what's going on there is Linux uses a much more optimized lock implementation than Mac OS does. I mean, there's these Futex locks, these fast user level locks, and you actually see it not as bad. Actually, if you go into those visualizations, there's a Linux link to see some plots done on Linux, so you can sort of see it there. Yeah.
I have a question. Do you know the threads implemented inside the Python interpreter using system level scope or process level scope? Your talk implies system level scope since they're actually scheduled by the operating system. And do you know, has there been any work to try using process level scope so that you don't actually have the system level overhead of swapping threads and such?
I don't know that people have done that, but they are system level scope. I mean, one of the things that people often do with threads is some of the C extensions like NumPy and things like that actually want to release the GIL and run in true parallel. So I think that's why that they're using the system threads there to do that.
Great talk. My question is regarding what constitutes a CPU-intensive process. I've got a system that uses threads extensively, actually everywhere. Some of the threads are using the threading library primitives for synchronization. So they might be, say, waiting on an event or a condition variable for a little bit and then waiting on another one, while other threads are doing I/O and things like that. Will those threads behave properly because they're using the threading library, or will they suffer from this priority inversion problem?
It's hard to say. Generally the CPU bound versus I/O bound is really just all about how much time does a thread spend waiting versus just running and not giving up the processor. I don't think if you're just doing a lot of waiting on things in the threading library, you're not really entering the CPU bound sort of category there. One thing I will say about the threading library, though, is all those lock primitives like rlocks and semaphores and things like that are actually implemented in Python. I think that's actually only recently started to change. I think Antoine also, did you re-implement rlocks in C? Yeah, he's nodding his head. So, there are some performance improvements that can be made there coming probably in Python 3.2 as well. So.
Thanks for the great talk. Do you know if setting processor affinity with running Python process with multiple threads will improve performance?
So the question is processor affinity. I don't honestly know, to be honest. I don't. It may prevent some of that thrashing around, but I'm not sure that people would really want to do that. Again, for some of these extensions, they actually do want to run on multiple CPUs, and so you probably wouldn't want to do that. Actually, in one of the tests that I looked at, I think some of like the compression code in Python, like bzipping and things like that, releases the GIL and runs in parallel. So you probably wouldn't want that generally.
Hi, thanks for the talk. Would it be valid to say that the behavior that we're seeing from Python programs is not communicated well to the kernel in the current interfaces that it uses? And if that's the case, is it worth trying to talk to the operating systems or figure out better ways to tell the kernel what's necessary from Python applications?
That is a really interesting question. I have not completely followed like the development of things like the Linux kernel on a day-to-day basis, but something like that. I mean, this is kind of a thing where it might make, if there was something available to give the kernel a hint, I could see it definitely being useful here. Now, I don't know whether the operating system people are even thinking about this or even aware of this. So. I don't know the full answer, but yeah, definitely. I mean, if there was a way to give a hint for that. I mean, operating systems have done that for other things. I think some systems like have hints where if you acquire like a mutex lock, you can actually give the system a hint to tell it that you're going to give it up pretty quickly so that it doesn't context switch you in the middle of holding the lock. So there are things like that around. Whether they can be applied to this, I don't know. All right, so no more questions. Okay, thanks a lot.